second. Okay, so everyone, thank you for attending today's seminar. Today, I'm very happy to invite Kevin Chen to join our seminar to present his special work about the robust and micro air robots, and especially his work on soft actuator artificial muscles. So before we start the seminar, I'd like to give you a brief introduction about Kevin. Kevin is a current D-Red Whedon Junior 41 Career Development Assistant Professor at the Department of Electrical Engineering and Computer Science at MIT. He received his PhD in Engineering Science at Harvard University in 2017, and his bachelor degree is in Applied and Engineering Physics from the Cornell University in 2012. His research interests including the development of the high bandwidth robust soft actuators for micro-manipulations and the locomotions. He has published a lot of top journals, including the Nature, Science Robotics, PNAS, Nature Communications, IEEE TRO, and the Journal of Fluid Mechanics. So right now, he is also recipient of the RAL 2020 Best Paper Award and IDO's 2015 Best Student Paper Award, and the Harvard Teaching Excellence Award. So this is like a shining background for Kevin. And so I'd like to, let's welcome Kevin to start his presentation. So I don't want to speak too much in front of him. And let's welcome Kevin, yeah.
Okay, great. Thank you so much for having me today. So I want to talk about agile and robust micro-aerial robots powered by soft artificial muscles today. There are two keywords in the title. One is micro, and the other one is soft. So I want to talk about micro first, and then I'll spend the second half of my talk to explain the keyword soft. So first, let's think about what are micro robots. When we think about robots, people usually think about large-scale robots. They think about humanoid robots, legged robots, or even trains or airplanes. They span the scale of meters to the scale of hundreds of meters. On the other end of the spectrum, there's very tiny robot made of the MEMS technology. They usually range from microns to tens of microns. What I want to focus on today is talking about insect scale robot, and specifically they range from 1 to 5 centimeter, and they weigh from 10 milligram to 10 gram. So as a quick example, when I was a student at Harvard, we worked on a project called the RoboBee, and that's very similar to a honeybee in nature. If you compare the weight of the robot and the flapping frequency of the robot, you will realize that it weighs about 80 milligram, and the flapping frequency is also very similar to bees in nature. And if you look at the timeline of this project, you can see a very interesting trend. We start by showing the robot can generate enough lift forces to lift itself. And then we start to implement control functionalities, such as demonstrating controlling hovering flight. And then we jump into interesting applications, such as teaching the robot to swim, teaching the robot to perch on compliant leaf, and also recently teaching the robot to impulsively transition from water back into air. So the interesting trend that you will see is that we first implement functions that large traditional robot can do, and then we transition to implementing functions that are difficult, if not impossible, for larger scale robots. So now I want to address several important questions together. The first question is, why do we study micro robots? And to me, there are two answers. The first one is usually we can use micro scale robots to achieve new functions. In this case, we demonstrate a very tiny micro scale robot is able to both fly in air and swim in water. And the second answer is that we can use micro scale robots as a platform to investigate interesting physics. In this case, by looking at the flow field generated by a flapping wing robot, we can infer about the lift and drag generation mechanism of this very tiny robot. So the second question that I want to ask is, what makes micro robot unique? And to me, the short answer is being small is different. And more scientifically, the inertial effect become much smaller and the surface effect become much larger. As a consequence, you have new properties. For example, the robot becomes robust because inertial effect is small. You can drop a robot from pretty far above and the robot sees very small change to its performance. And the second property is all of a sudden you can leverage surface effects. So in this case, you show that your robot can jump out from the surface of water. Again, something very challenging, if not impossible, for larger robots. The next question that roboticists want to ask is, well, what are the potential applications? In the short term, we can think about using a micro-scale robot to do search missions in a cluttered spaces. In this case, we are trying to demonstrate a micro-scale robot can climb inside of a turbine engine. And if we put a small camera on the micro robot, then you can look for cracks inside the turbine engine. In the longer term, you can think about using a swarm of micro robots to do search and rescue missions in this very complex space, right? There's fire, water, and cluttered spaces in this picture. Of course, this is a very far-fetched picture. I would say we are at least 20 to 30 years away from this, but toward the end of this talk, we're going to come back to this larger scale picture and think about what challenges have we been able to address in the past 5 years or so, and what are the lingering challenges that we still need to tackle in the next 10, 15, 20 years. So today I want to focus on 3 projects. The first project involves explaining a hybrid aeroaquatic micro-robot that can both fly and swim. The second project involves explaining about a hybrid terrestrial aquatic micro-robot that can work on the surface of water and also on land, and also transition into water. So that's pretty much the first part of the talk. In the second part, I will focus on entirely different project in that we will focus on our recent work in creating soft actuated aerial robot, how we can use soft artificial muscles to enable flight, and what new properties can be enabled in those micro-scale robots. So first, I want to talk about how flapping wing works. Okay, as for background, we created a micro-scale flapping wing robot that has 2 degrees of freedom. So the robot has a wing stroke motion that's actively controlled by a piezoelectric actuator. And it has a passive wing pitch motion that's simply passively mediated by the compliant flexure. So this system is under-actuated. We not only need to actuate the system, but we also need to rely on the fluid structure interaction to generate the lift and drag forces. We use a high-speed camera to capture thousands of those flapping wing videos. And the challenge is how do we measure the lift and drag forces, but also the instantaneous flow field. So I don't want to spend too much time to focus on fluid mechanics today. I think there's a lot of you here focusing on those. And really, I'm trying to highlight the problem and look for collaboration opportunities. One of the things that we used to do is that we use particle image velocimetry techniques to observe a flapping wing that's about 1 centimeter long, and it operates in the order of 200 hertz to 500 hertz. So we shine a laser sheet to illuminate some of the oil particles in this plane, and then here is a sample video that shows the motion of those oil particles. And by computing the cross-correlation of those images, you can obtain the flow field and the vorticity field. So here's an example showing you the growth and shedding of leading edge and trailing edge vertices came from a flapping wing. And by analyzing the circulation around those vertices, you can infer about the lift and drag forces. One of the things that we spent a little bit of time into was numerically solving the incompressible Navier-Stokes equation so we can estimate the lift and drag forces. So we implemented both a 2D simulation a couple of years ago, and we also sort of take a dab at implementing a 3D CFD simulation. So the idea in the 2D simulation is, again, instead of focusing on the motion of the entire wing, we just look at the motion of a particular wing chord, and you project that wing chord onto a 2D plane. So you can look at the wing stroke motion, which now becomes a horizontal or planar translational motion, and the wing pitch motion, which is passively mediated by the compliant flexure. So in the next video, we are going to show you a simulation result. We are showing you the X and Y component of the flow field, the pressure field, and the vorticity field. So if you spend a lot of time comparing your simulated flow field with the measured flow field, quantitatively they're quite similar. But in reality, in the 2D simulation, the shed vertex tend to stay in the fluid for much longer, and it has a much larger influence on the lift and drag force generation that usually can create a modeling error that's on the order of 30%. So we also implemented a 3D CFD simulation. The 3D simulation was way slower, but what it was able to show us is a significant span-wise flow that can stabilize the leading edge vortex. We didn't actually get to do too much work with the 3D CFD because we didn't have too much experience with that, and it takes very long to run. So it would be great to see if some of you guys are interested in also studying the flapping wing motion of a small insect or robot at this scale. Okay, so what we wanted to do, though, using those experimental and computational tools, was to focus on implementing new functions in robot. So one project or one question that we came up with was asking ourselves if there is any similarity between flapping in water versus flapping in air. And if there is similarity between those, then can we teach the robot to use the same set of actuators and wings to also effectively move in water? So we have came up with a project in which we aim to teach the same robot to be able to take off from land, fly in air, transition into water, swim in water, and then possibly transition back in air and eventually land on ground. Thinking about this project, we have identified two major challenges. The first one is, how do we use the same set of actuators and wings to achieve multimodal locomotion in air and water? And second, how do we overcome surface tension effects so that we can allow the water to the robot to transition from air to water and eventually also transition from water back into air? So let's think about the first challenge, that is multimodal locomotion. To approach this challenge, we first look into nature for inspiration. Puffins are really amazing animals. They can fly in the sky. In this case, they take a dive into water. Once they're under the water, they modulate or change their flapping frequency so they can swim very effectively in water and chase for prey. We look at this inspiration and started with a very simple quasi-static scaling analysis that basically imposes the robot has to generate a similar force in water and in air. And that leads us to a frequency scaling relationship that predicts the robot operating frequency in water. And then we look at the change of the Reynolds number. And to our surprise, the two systems have very similar Reynolds number. And that really implies the system can generate very similar forces. Using our numerical simulation, we showed that the two systems are actually going to generate very similar forces and torques. And in fact, we also showed in experiments that the force generation is quite similar in the two systems. So we insulated our robot. We conducted flapping experiments in air and in water by changing the flapping frequency. Now, I just want to say that this is a very important result for us. The fact that you're seeing similar flapping kinematics really implies the two systems are generating very similar forces. And the reason is that the pitch dynamics is passive. If those two systems are not being able to generate similar forces, then the pitch motion wouldn't be very similar. So this experiment informs us that we can generate similar forces in water. And therefore, we start to look for demonstrations that can lead to the robot to swim in water. So we formulated a full 10 degrees of freedom model that characterizes the stability condition of the robot. And through conducting experiments, we show that if we reduce the flapping frequency of the robot by about 10 times, then we can achieve passively stable ascending swim in water. So the next video I'm going to show shows this robot is able to passively, stably swim to the air-water interface. And that's a quite impressive result, right? Without any feedback control, the robot was able to rely on the drag force on the robot body to stabilize itself. And that is something that's very challenging for the robot to fly in air. So in both simulation and experiments, again, we show that without any feedback control, all we need to do is to set the robot flapping frequency and amplitude in a specific range, and the robot can swim passively upright towards the air-water interface. And that is very different from what we did for controlling the robot in air, which constantly requires motion tracking and feedback control. So about 5 years ago, for the first time, we are able to show that a very tiny robot, about 0.07 gram, is able to fly, take off in air. And at that time, it really has to crash into the air-water interface. Once the robot transitions into water, we turn on the robot at a much lower frequency, and the robot will be able to swim back to the air-water interface. So that was a very exciting moment for us, because for the first time, we demonstrated that even very tiny inside-scale robot can do multiple things in multiple environments, and this is quite challenging for larger-scale robots. There's one limitation that you probably can notice from this video, which is that the air-water transition was not very elegant. The robot essentially has to crash onto the water surface. So that motivates us to think about the challenges to enable the robot to do transitions between two environments and consider the influence of surface effects. So the second challenge we want to overcome is teaching the robot to make transitions. And again, let's try to identify the major challenges. So to us, there are several challenges. The most important challenge is that the surface tension effect is 12 times the robot weight, which means that it is much larger than the robot's maximum lift. If you just want to sort of teach the robot to flap its wings and somehow impossibly transition from water into air, that would be extremely challenging, because the water surface acts as a wall and it pushes down the robot. So direct water to air transition is impossible through just flapping. So how do we overcome this problem? So to overcome this problem, we sort of think very hard about the property of surface tension. And we realize that in fact, surface tension is singular, meaning that it only exists at the air-water interface. And the solution is to come up with an impulsive mechanism. Specifically, we want to have a two-step transition process. In the first step, you gently split water into gas through electrolysis and use a little bit of buoyancy force to push the fragile part of the robot out of the water surface. And that is the wings and transmissions. And in the second step, you're going to use the collected mixture of gas, which is composed of hydrogen and oxygen, and you're going to ignite the mixture of gas and use as a fuel to impulsively jump off the water surface. The combustion process hopefully will complete in a very short time and generate a very large force that is able to break the air-water interface, so that you can use an impulsive mechanism to generate a large force to break the air-water interface. So now that brings us to the new robot design. Compared to the old robot, the new robot is about twice as heavy. You probably can notice that you have 4 buoyant outriggers for maintaining the stability of the robot on the water surface. It has new wings for generating more lift. And more interestingly, it has an impulsive takeoff functionality that is enabled by a gas collection chamber. And I want to explain the functionality of all those components. First of all, if you don't have a buoyant outrigger for maintaining the balance on the water surface, then the robot is unstable when it reaches the water surface. The water surface pushes down, exerts a torque, and the robot tilts away from the water surface. If you have a buoyant outrigger, what you can see is that those buoyant outriggers can maintain stability, and it can allow the robot to face upward and prepare itself for this impulsive takeoff. I think perhaps the most interesting part is the micro chamber that allows the robot to do the impulsive transition. If we zoom into the chamber consists of a titanium and polyimide top piece, 4 polyimide and carbon fiber side pieces, and a multifunctional component that's responsible for splitting water into gases, but also for igniting the gas and triggering the combustion process. So first, if I put this small device in water, and if I input a very low voltage on the order of 3 or we are going to turn on a high voltage on the order of 200 volts to trigger a tiny spark, and this spark will be used to ignite the mixture of hydrogen and oxygen. So now let's try to put everything together. First, we start the robot in the bottom of a tank. It will swim to the air-water interface. And once it reaches the air-water interface, you're going to turn off the robot wings, and we're going to turn on the gas collection chamber so that we are going to start capturing gases and slowly pushes the robot wing out of the water surface. Once the robot wings are out of the water surface, we are ready for impulsive takeoff. So the next video is going to be very quick, and so I strongly recommend you to sort of focus on the first part of the next video. Okay, once the robot is ready for takeoff, we ignite the mixture of hydrogen and oxygen, and as you can see in this case, the combustion completes within 1,000th of a second, right? Within 0.001 seconds, the combustion completes, the robot breaks the air-water interface. And in fact, we have spent a lot of time to make sure that we can reduce the pressure and not create a large force that can explode the robot into pieces. But this actually is limited. The robot cannot immediately fly after impulsive takeoff because of all the water that's on the robot. So the robot has to passively land on ground. So this video will play in real time. It's also very quick. You will see that in real time, the robot takes off and lands. This entire process takes about 0.5 seconds to complete. The robot is passively stable, so it will take off and then it will passively land on ground. Okay, and after that, the robot really has to wait for about 10 to 15 minutes, and then the robot will be able to take off and fly again. So in summary, we have created a 175 milligram microscale robot that is able to fly, that is able to swim, that can transition from air to water very easily, but also more impressively can transition from water to air through a combustion, and can also passively land on ground. You can repeat this process, but you couldn't immediately allow the robot to fly immediately after impulsive takeoff. So the important takeaway from this project is that it really shows, although microscale robots are very tiny, they truly can leverage interesting physics to do very interesting things in very complex environments. Following the same thread of thought, now I want to introduce a second project in which we are trying to teach a crawling robot to do multiple things in complex environments. In the previous project, we spent a lot of time trying to show a microscale robot can overcome a surface tension force that's 10 times the robot weight. This is very challenging. We have to use combustion to realize that. On the other end of the spectrum, as humans, we barely feel surface tension at all, right? The surface tension, in fact, is less than 0.1% of our weight, so it's really not influencing us that much. If somehow you can create a robot that's in between those two examples, specifically if this robot can be on the order of 1 to 2 grams, and if its contact length with the water surface is on the order of 10 centimeters, then the surface tension force and the robot weight are on the same order. And now you can think about interesting functionalities by leveraging the relative magnitude of those two forces. So the question that we want to ask ourselves is it possible to control the magnitude of surface tension? And if it is possible to control surface tension, what robot functionality can we enable? So in this case, we decided to create a new project in which we want to teach a crawling robot to do multiple things. Specifically, we want the robot to work on land, on the surface of water, controllably transition into water, and eventually return back on land by transitioning out and then continue to crawl on land. And again, let's identify the major challenges. The first challenge is, how do we teach the robot to both float on the water surface, but also controllably transition into water? And the second challenge is, how do we allow multi-phase locomotion, right? Which means, how do we use the same set of actuators to both move effectively on land, but also move effectively on the water surface? So that brings us to the new robot design. We used a pretty mature platform at Harvard we designed a new electrowetting footpath for the robot so that we enable the functionality of working on the surface of water and also working underwater. Okay, so to float the water on the water surface, we used a combination of surface tension forces and the buoyancy induced by the surface tension forces. And in this design, the surface tension force is about 25% of the net upward force, and the buoyancy force is about 75%. Frankly, it's not very challenging to float a tiny robot on the water surface. I think what is challenging is to enable controllable transition without resorting to new actuators or new moving parts. So that motivates us to think about a new physical phenomenon, electrowetting. And the key idea is that we are going to make our electrowetting footpad with a thin copper foil that's covered by a dielectric material such as parylene or Teflon. And when we want to teach the robot to sink into water, we command a high voltage on the order of 500 to 600 volts, which will induce a change of the contact angle. Once we induce this change of contact angle, both the surface tension forces and the buoyancy force will reduce, and that will allow the robot to transition into the water surface. So very quickly, I just want to show you that in this demo, right, a floating robot was able to transition into water surface as soon as we turn on this high voltage to the footpad. And this is a repeatable process, right? We don't need to spend a lot of energy. Just a tiny bit of energy is sufficient to change the contact angle. So we have solved the first problem. The second problem is, how do we teach the robot to move on the water surface? I want to start by saying that a typical crawling gait for working on the surface of water is very ineffective, right? Here we are trying to use a gait in which we are trying to teach the robot to work on land. As you can see, because the motion is more or less symmetric, and because the Reynolds number is very low, I think it's on the order of maybe 50 to 100, you're really not generating a lot of forces. So instead, what we want to do is to look into biology for inspiration. So when we look at bioinspiration, a diving beetle is something that's on the same size that can swim very effectively. And specifically, it split its swimming motion into two phases. In the power stroke, the robot or the beetle is going to fully extend its leg and push down very fast to generate a large propulsive force. And in the retraction phase, the beetle will slowly retract its leg and slowly recover to the nominal position. And taking inspiration from this picture, we created a passive flap that uses fluid structure interaction to do similar things. In the fast power stroke, the flap will remain fully engaged so that it can generate a large forward thrust. But then in the slow recovery stroke, the flap will collapse so that we will minimize drag. In both experiments and simulation, we are able to show that we can obtain very similar kinematics so that we can induce asymmetric flapping motion, and with the hope that we are able to induce asymmetric flapping forces. With this driving strategy, we show that our robot can swim on the water surface at a speed of 2.5 centimeters per second, which is again comparable to insect at this scale. And now I just want to put everything together and show you an interesting robot video. In this case, the robot starts on land. It walks onto the water surface. It will swim to a targeted site, right? So it already transitions from land to the water surface. And once it reaches the targeted site, the robot will transition underwater. So if you focus on the side view, now the robot sinks underwater. Once the robot is under the water, it will try to climb this incline to return back onto the land. Something I didn't have a lot of time to explain today is it's actually very difficult for the robot to transition back from underwater to land. And that is sort of the most part of time that we spend in this project, thinking about how to overcome surface tension effect, both transitioning into water, but also transitioning out of water. But as you can see, eventually the robot can return back onto land. So it starts on land, swim on water, transition into water, and then eventually return back onto the surface. It comes back to land. Until very more recently, we start to think about multimodal locomotion in that we are thinking about using surface tension forces to also teach the robot to climb on inverted and inclined surfaces. Not only do we want the robot to use surface tension effect to locomote in water, we also want to climb walls and ceilings. And that is something that we have just started to work on, which is, again, using a thin water film to create a large adhesion force, but a very small friction force, so the robot can remain adhered to a surface and use that to crawl. For the interest of time, I'm not going to focus on too much on the fluid mechanical analysis, but I just want to say that by using a combination of capillary adhesion theory and lubrication theory, we're able to show that we can generate a large normal force, but a very small friction force. And that allows the robot to very effectively crawl on inverted surfaces, which shows a significant improvement over the state of the art. Okay, so that is the first part of the project. That is sort of the main part of my work when I was working at Harvard. The major theme of my previous work was thinking about showing how very small robot can do multiple things in very complex environments, just like insect, and show how they're very unique compared to large-scale systems. In the remainder of my talk, I want to focus on an entirely different project, which is a robot powered by soft artificial muscles. I want to first start with a short motivation. In the very long term, what we really want to do is to create a swarm of ubiquitous and multifunctional microrobots that can collectively accomplish very complex tasks. So far, what I've shown you today is that microscale robots can operate at high frequency. They are very precise robots. And in fact, they have very complicated motions. However, we still have challenges in terms of thinking about sensing and control. We still have challenges thinking about putting a battery and sensors on board. But to me, there are a lot of challenges that we've been overlooking in the past few years. Specifically, microrobots are fragile. They are mostly powered by rigid actuators, and they can't collide into obstacles like what insect can do. And in addition, because they're very precise, it takes a lot of expertise to train a graduate student to make one, and it takes forever to make one. So that really precludes us from operating a large number of them together. To solve this challenge, I propose that we look into a different field for solution, which is soft robotics. People know how to make a swarm of soft robots very effectively. And people know that soft robots have large motion and they're very robust. They can effectively interact with the environment. They have a lot of sensing and control strategies. In the past few years, most soft robots are controlled open loop. Nowadays, a lot of them now have closed loop controls. In terms of power sources, not only do soft robots can use a battery, they often use pneumatic sources or even chemical sources. But soft robots also have a lot of key shortcomings. Specifically, most soft robots are slow. They operate at a very low frequency, and they have very low power density. And in addition, because they have large motion, they're usually not very precise. So the functionality of soft robots are usually far inferior than rigid robots. My research goal at MIT is to merge those two fields and create what we call microscale soft robots that hopefully can be both very agile, but also very robust. So what we did over the past few years is creating a new class of microrobot, which we call hybrid soft rigid microrobot. Those microrobots are powered by soft actuators, but they have rigid appendages, so they can effectively interact with the environment. As an example, we created a flying robot that is powered by soft artificial muscles. This soft artificial muscles can operate at a high frequency. It has large strain on the order of 10 to 20% as opposed to the 0.2% of piezoelectric actuators. And it's very robust against collisions, which allow the robot to collect the things and interact with the environment. In terms of fabrication, because we are now making a soft actuator, the assembly precision can be reduced significantly, probably by a factor of 10, which really allows us to make a large number of them very effectively. But on the other end of the spectrum, there's still very high precision component like transmissions and wing hinges, so we can precisely control the flapping kinematics and generate good lift and drag forces. And finally, because the actuator is soft, it's not only robust, it can also be used to detect collisions in air, which really allows the robot to achieve new flight capabilities that I will show in the next few slides. On a very high level, the robot consists of key components such as the airframe, robot transmissions, wing hinges, and wings. And the key difference is now it has a soft artificial muscle as the robot actuator. Compared to the piezoelectric actuator, this soft actuator sort of has a similar physical scale. It has a slightly lower bandwidth. Instead of being able to operate at 1 kilohertz, the actuator can operate at 500 hertz. But the benefit we get is a much larger strain on the order of 10 to 15%. And in addition, because it is soft, it's intrinsically tolerant to assembly error, which really allows us to make a lot of them very effectively. From a conceptual design perspective, we impose 3 conditions. The first condition is that the robots need to generate enough forces so that it can lift itself. The second condition is that the actuator has to generate enough forces so that it can offset the drag force induced by air. And the third condition is that we have to think about how to make the wings so that the wing inertia is close to the resonance of the actuator. Don't worry about the exact formulas, but I think those high-level ideas of design is very important. And what I want to focus on today is explaining to you the property of the soft actuator. The soft actuator's performance is mainly characterized by 3 parameters: bandwidth, free motion, and block force. To think about the bandwidth, we first look at the electrical bandwidth of this actuator, which is modeled by a RC circuit. And we measure that the effective resistance and capacitance of our actuator is on the order of 200 kilo ohms and 1.1 nanofarad, which translates to a very small electrical constant, which this electrical time constant infers the robot was able to operate at a very high frequency. So the operating frequency of the actuator is not dominated or limited by the electrical resonant frequency, but rather the mechanical resonant frequency, which is on the order of 500 hertz. When we characterize the actuator, we first measure the block force. We place the soft actuator under a force sensor, so we can measure the 0 to peak motion of force. And in this case, we realized that a 0.1 gram actuator was able to generate a maximum force that's on the order of 0.2 Newton. In addition to that, we also measure the free motion. The free displacement can be measured by shining a laser on the top cap of the robot and looking at the oscillation or the velocity of the actuator, and then you can integrate over the velocity to back out the free motion of the actuator. So in this case, you can see that the system, although linear, it can be approximated by a second order system. And if you operate the actuator at its resonance, then the actuator motion can be as large as 20% in strength. And now if you multiply the operating block force and free displacement, you can estimate the energy density of the actuator. And if you multiply that by the frequency, you can estimate the power density of the actuator. In this case, what we see is that the maximum power density of the actuator exceeds 500 watt per kilogram. And based on our previous analysis, what we notice is that as long as the power density is larger than 200 watt per kilogram, it is possible to enable flight. So we incorporate our actuator into a flapping wing robot. And in this video, we demonstrate the robot is able to flap at 280 Hertz, and it can achieve a large peak-to-peak stroke motion, which means that it can generate enough forces to lift its own weight. So that's what about 2 years ago. For the first time, we showed that a very tiny self-actuated robot was able to take off very briefly. And that was a super exciting moment for us. It shows self-actuator has enough power density to enable flight. But as you can see in those two videos, right, from a roboticist perspective, it's really not very impressive. The robot flips over in 0.1 seconds, is not intrinsically stable, and it flies to a top height of probably 1 or 2 centimeters. So it's really not very useful. If you look at the same composite image that shows the same video, again, the robot takes off and flips over really quickly. What we did next was to think about stability. How do we ensure the robot can fly upward without feedback control? And that requires us to use a physical phenomenon called precession. And the idea is that if you can induce a fast rotational motion relative to the robot's yaw axis, then you can use the precessional motion to stabilize the robot. Again, to see this, you have to go through the mathematical analysis and look at the relative contribution between the moment of inertia tensor and the yaw torque. But for now, let me just say that in both simulation and experiment, we are able to show that the robot can indeed achieve passively stable upright flight. But again, without any feedback and control, right? The robot was able to use this precession effect so that it can fly upward without any sensing and control. And in fact, in this video, the robot achieves a flight speed of 30 centimeters per second, which is already as good as the state-of-the-art rigid robot that's lower than a gram. In both experiment and simulation, again, we've been able to observe a similar effect. So in the previous videos, we showed that with 1 unit of the robot, you can achieve passively stable ascending, or you can achieve takeoff flight. With 2 units, you can achieve passively stable ascending flight. And with 4 units, you can achieve controlled flight. So the core question is, how do we enable the robot to hover at a particular place? How do we incorporate feedback? Again, without going into the details of the controller design, let me just say that as of probably 2 years ago, for the first time, we are able to show a soft power robot was able to achieve controlled hovering flight. In this video, the robot flies for about 15 seconds, and if it remained quite stably at the hovering set point, and if you look at the flying air, the drift in the XY planes on the order of 3 to 4 centimeters, and the air in the Z dimension is about probably 1 centimeter. So up until now, we've shown that soft robot can demonstrate most of the functions that rigid robot can do. The next question we should ask is, what additional functionality can we enable? The first thing that comes in mind is collision robustness. In this case, you can repeatedly run a wing into an obstacle, and the actuator sees small damage to its performance. In fact, by monitoring the current in the actuator, you can sense collisions. And this is very effective because this allows us to close the loop. If the robot is flying, as soon as it collides with something, we can notice that collision really, really quickly and start to think about feedback control ideas. And the second thing is, because the robot is robust, for the first time, we are able to show the soft robots can not only fly by itself, but also fly in swarm. In this simple demonstration, we intentionally fly 2 robots together, and we intentionally fly both of them into walls just to demonstrate they're very robust. And in other videos, we also show the 2 robots collide with each other in air, and again, suffer no damage physically. The next thing that we have been starting to think about starting from last year is aggressive stuff to do. For example, we are taking inspiration from a very famous robot in MIT, the MIT Cheetah. MIT Cheetah can do multiple things. You can kick on it and you can try to recover stability, or you can try to do a somersault, which again demonstrates the agility of bio-inspired robot. our research question is, can we replicate similar functions in our flying robot? So as of probably 6 months ago, our team was able to show that this robot, it can recover from in-flight collisions. In this first video, we show that we try to gently hit on the robot, and the robot was able to recover to the flying set point. In the second video, we try to be a little more aggressive. In this case, now we try to poke the robot actuator, and later we try to poke the robot wing. As you can see, in both cases, the robot is able to return to the hovering set point. In the third video, we try to be even more aggressive. We try to hit the robot really hard. In this case, the robot couldn't recover, but it uses the ground to recover to its set point, right? It collides on ground and bounces back, and then it recovers to the hovering set point. So again, in all those 3 videos, we've been able to show that the robot can survive collisions, but can also recover from these in-flight collisions. You can hit the robot airframe, you can hit the robot actuator, you can hit the robot wings, or you can introduce a very large impulse such that the robot needs to bounce on the ground and then recover. The next thing we want to think about is, can we teach the robot to do a somersault, right? This is a great challenge because that would show insect-like flight agility. In simulation, we show the robot was able to take off, and it will accelerate upwards, try to do a somersault, and then it will try to recover to the hovering set point. Okay, so after we show that this maneuver is feasible in simulation, we try to demonstrate it in experiments. So again, I'm going to play this demo in real time. So I recommend you to pay attention to the first part of the next video. In real time, the robot flies up, hovers, try to do this somersault, and return back to the hovering position. And now let me show you the same video. Again, the robot takes off and it hovers around the set point for 2 seconds. And then it tries to accelerate upwards, okay? And once it has a large upward speed, it tries to do the somersault, and then it tries to recover. In this case, it couldn't really recover before hitting the ground just because our old flight arena was a little bit small, but then we are able to hit the floor and then return to the hovering set point. And this demonstration is split into several steps. We take off and hover. We try to ascend as fast as possible. And then we try to make a somersault within 0.16 seconds. That is by far the fastest somersault that any flying vehicle can do, simply because the scaling of the robot. And then we try to recover. And finally, this robot tried to return to a hovering position. This process is very repeatable. We have repeated it 5 times and demonstrate that the robot is not only robust to collisions, but also can reliably demonstrate it for many, many times. So in summary, we have created a soft aerial robot that is both agile and robust. By robust, we mean that it can survive in-flight collisions. And by agile, we mean that it can do a very fast somersault. And in fact, the maximum ascending speed exceeds 70 centimeters per second, much faster than any other sub-gram aerial robot. So now we are also thinking about continuing to improve our robot. And eventually, I believe one day, the soft robot will be comparable to the state-of-the-art rigid robot. So if I look at the state-of-the-art rigid robot, they really have very great performance in terms of power density, lift-weight ratio, actuation voltage, and efficiency. And the ultimate goal of sub-gram flying robot is, of course, to put batteries and circuitry on board. If you look at the first version that we created 2 years ago, right, the power density is about half of the state-of-the-art. The lift-to-weight ratio is about 25%, actuation voltage is much higher, and the efficiency is about 15% lower. So I would say we are still a very long way from catching up to the state-of-the-art in some of the core performance metrics, but we are making progress really quickly, right? As of 6 months ago, we published work on the second version of SoftFly, in which we are already catching up on the power density. Our lift-to-weight ratio now becomes 50% of the state-of-the-art. The actuation voltage is worse. That is something we still need to work on. And we also see an improvement of efficiency. And I just want to say that hopefully within a few months, we will released the third version of our softfly. And that is a very exciting work to us because we've been able to significantly improve the lift to weight ratio and significantly reduce the actuation voltage. To us, that really drives us a step closer to achieving power autonomous flight in soft-aerial robot. In addition to thinking about power autonomy, we're also thinking about new designs of soft robots, such as a dragonfly-like robot, thinking about new form of aerodynamics involving forward and backward interaction. Now, that is something I really want to collaborate with some of the scientists working in the area of CFDs and fluid mechanics. And also, we are thinking about other forms of soft-powered robot. In this case, this is a compressed air-powered flying robot, hovering but flapping at 165 Hertz. This is in collaboration with Professor Rob Shepard at Cornell. We are ultimately thinking about flying a large number of micro-scale robots, and we are also thinking about teaching micro-scale robots to do interesting things, such as perching on tree branch. With that, let me conclude by saying that I'm very excited about the field of micro-robotics. I think we are very long way from this picture of using a large number of micro-scale robots to do search and rescue in very complex environment. But just imagine, right? If I have a large robot that have 10 kilograms of payload, that would translate to over 100,000 micro-scale robots. Imagine using such a large number of micro-scale robots to do collective sensing, to do searching, and that will be a very promising application in the next 20 to 30 years. With that, I want to thank my previous advisors, Professor Ron Wood, David Clark, and Jane Wang. Over the years, I have the pleasure to work with a lot of collaborators, and they're now all assistant professors or associate professors at top institutions worldwide. And finally, I have a couple of students now, and they're now leading some of very exciting projects in our lab. With that, let me end here, and I'm happy to take questions. Thank you.
Oh, thank you, Kevin. This is a great talk. Like, I really like your research, like combine like fundamental theories and those robotics together. This is something like I dream about in the future. So let's take questions, start from like audience first. Maybe is there any question from audience? Please raise your hand or just type your question in the chat channel. Maybe audience are trying today. So Disha, do you have a question?
Let me unmute myself. Yeah, Kevin, I actually have a lot of questions, but I think like it's a good time to like maybe even to get together sometime, because the first video, the couple first video you're showing is like a puffing. Like we do also like a robotic can both trying to both fly and swim, and puffing basically like using more like agile control of the vortex of the thing. But particularly, I'm interested in one of your work is that like the break through the like an area and like water like interface. So before you have shown that through this like a combustion of like motion, that it's able to break through this like a strong like capillary like force.
Right.
But you ended that story like saying that like the recovery from that like impulse force is tremendously like strong and need take some time for the baby to recover. So any like follow-up work on that in the way that apart from like basically using impulse force, like have the things like to points like the floating, and is there also thing like say like maybe the surface can be hydrophobic or something in the way, then using the like flapping foil to like then take off like slowly like So is there any additional thoughts on this, have follow-up work on this? So
sure. So I can tell you a little bit more about our struggle with that problem. Essentially, I think we've seen many biological examples in which for example, flying squid or flying fish that can sort of just transition from water into air, right? And I think that's largely because at their scale, the inertial effect is much stronger than capillary effect. So it's much easier for them to just transition without even worry about the capillary effects. When we started working on that problem, we also started with looking into nature for examples. There are small beetles that can dive and sort of, they can fly, they can dive, and they can come back to air. And very interestingly, if you observe what their strategy is when they dive, they carry a little bit of air with them. And that air bubble sort of forms a small layer around them so that they shield them from getting completely from water being sort of trying to get into them. But even for them, when they are trying to do the transition is a gradual process, meaning that they first swim to the air-water interface, they try to dry themselves a little bit, they stay on the water surface for a little while, and then they take off. So in some sense, I feel like at this scale, trying to think about this impulsive transition idea was in fact very difficult. So in some sense, this impulsive transition is not very energetically efficient, and it's also not what insects are doing. A better solution perhaps is to learn what insects are doing, which is to say, maybe I don't need to transition in 0.1 seconds, right? Maybe I can afford to swim to the air-water interface, stay there for a couple of seconds, just wait for myself to dry, and then just open my wings. My wings are probably hydrophobic, and then I can just swim upwards. And in fact, that is what leads to the second project. We worked on the impulsive transition. We realized it was way too difficult. And then we realized that maybe doing this impulsive transition thing may not be as effective as thinking about tunable capillary effect, thinking about tunable contact angles, and that leads to the crawler robot application, which is using capillary effect and electrowetting to controllably move between water and above water.
I think if I may give instead of a question, a comment on that, because there may be something I want to debate or discuss with you, maybe in person, is that you mentioned that the animals coming from the water to the water air surface and they take off. And the bubble thing, puffing also do that, right? They have the air being trapped in their wings, and then release that as a rocket to go to the surface. But they don't just jump right away. They come out of the surface, chill a little bit, and then use their paddle to start again momentum to have the lifting surface of the lifting force for their body to take off. So just as you said, maybe there's not, maybe animals, it's gonna be too difficult, and there's no necessity for them to really just propose themselves out of water in short momentum, but they can being gradually come to the surface and then somehow paddle to gain some a speed or both laterally or horizontally, and then slowly take off in a more agile way. So in a way, it will be more easy for them to control their body motion in the air, and vice versa, coming to the water. So that's some comment I'm having really thinking about, because I'm thinking about a little bit larger model as puffing, goose, and geese, these type of things. So just a comment on this. So
yeah, certainly, and I totally agree. So again, coming back to the idea of trying to do this very slow transition, one thing at that time, one of the limitations we have, and we still have in small scale robot, is actuation is still hard. So if you compare small scale robot to insects, you will realize that insect has many muscles, whereas we can only afford to put in 2 or 3. So if you think about this transition, I think being able to morph your body is much more effective, right? If I can tack my wing in, I can reduce a lot of surface tension effect. But the fact that I want to sort of tack my wing in or close my wings, take another actuator. and being able to morph your body in small scale robots really requires tiny scale and reliable muscles that we simply don't have. So I think a lot of the demonstrations in microscale robots is of course driven by inspiration from biology, but also in part limited by the available technology in building robots and in building actuators at this scale. So it's a lot of times, I think in summary, it's a compromise between what we want to do and what we can do.
Yeah, I totally agree. If I can ask one more question, like Zhongqiang, since you're moderator. So it's that, so right now it's a lot of control, if I understood it, through like, the camera, like to know like the position or the thing. So what about like, have you started putting some like a micro sensing like on these robotics? Because I see actually Chen Yu is here. So I think Chen Yu have done a lot like, so like other like a smelling or these things. Is there like, so basically like, say, because the bird like, or like the animal can like sense the pressure around it, like, what do you thought on like putting sensor like into micro sensing into this micro like robotics?
Yeah. So again, I think it's a very important topic, right? In fact, if you think about our long-term objective is to achieve power and control autonomous flight, not relying on both outboard battery and outboard sensors. What I didn't show you is that now when the robot flies, we have huge motion capture cameras around there to figure out the position, which we use as ground truth. There has been work at Harvard trying to incorporate MEMS sensors on the robot. And I can say that, for example, IMUs and things, if you put a small IMU on this robot, the problem that we see is flying robots have a lot of oscillation compared to quad rotors. So the drift problem is quite significant. So people have tried pressure sensors, people have tried IMUs, and people have tried small cameras to do vision control. I think all of those can work probably on the order of seconds, meaning that it is okay to do low-level control for a couple of seconds, but then the drift of the sensor will take you elsewhere. So sensor fusion, I think, is really the future of what we want to do, which is rely on a combination of sensors and slowly replacing the motion tracking system. But yes, definitely, if there is audience in this talk who are interested in creating micro-scale sensors, that's something that we are very happy to try on. And in fact, we have a fairly good motion tracking system at MIT now. So it will be very easy experiment for us to compare what the motion tracking system is giving us versus what we can predict from those sensors. But yes, that's definitely something we are looking for right now.
I'll reserve my last question. Like, I see some people raise hands, like, if I have some time. So.
Yeah, I think, yeah. So please, Hans, please ask your question.
Hi, thank you for your very interesting talk. I'm from Delft, University of Technology. A lot of the problems or challenges that you've been talking about are related to scaling. So energy densities, use of energy in aerodynamics. So I was wondering whether or not the challenges you set with this scale are prohibitive in advancing some of these things. So you said it would be good to have 10,000 micro robots, but maybe 10 times the weight, you would have 1,000, which would still be very useful. So, what is your view on this, on the scaling aspect of this?
Sure, of course. So again, I think most people in this field are working mostly on the robot structures and aerodynamics. I can say that now, if you look at especially the state of the art, most of the sub-gram micro aero robots are in the range of 0.1 grams to 0.2 grams. But as you've said, the prohibiting technology, I think now the bottleneck is more in the power electronics, which because most actuator requires high voltages, and the battery. The smallest battery people can find is about 0.3 grams. And also, what I want to say is, if we look at one level up, like those functional quad rotors, small quad rotors, they usually weigh about 10 grams-ish. And that is because the limits on the electromagnetic motors. I would want to argue that when the weight of the motor are smaller than 1 gram, they become less and less efficient. So if you think about quadrotor, they at least require 4 motors. So the minimum weight I can think about for a quadrotor is on the order of 5 grams. So I think there's a huge space still, and I totally agree with you. If we want to push for micro scale robot, we shouldn't just wait for 20 years to wait for all the technology on batteries and power electronics to catch up. What we should do is to do a conversion study, meaning that how about if we scale up the robot size a little bit, depending on we still have some of the favorable quality that we have. For example, the diminishing inertial effect, the robustness when the robot wing hits onto flowers, etc. So in our lab, what we are trying to work on, maybe in the next 5-7 years, we are working on power autonomy, but we are definitely not, like a lot of my colleagues, restricting ourselves to maybe robots on the order of 0.1 gram or 0.2 gram. Instead, the flying robot, the 4-unit robot that I showed you today weighs about 0.6 gram, and the payload that they have is on the order of 1.2 grams, right? So with 1.2 grams of payload, that's almost a factor of order of magnitude more payload than existing sub-gram aerial robot. And then you can think about more complex circuitry, heavier battery, etc. But what we want to make sure is at that scale, 1 gram, 2 gram, like a heavy beetle, we still have those collision resilience capabilities such that we can still do insect-like maneuvers, such as landing on flowers or pollination or collaborative flight. So in some sense, yes, definitely. I think we are now restricted to 0.1 gram, 0.2 gram flyers. We are thinking about a space in which we are still significantly lighter than smaller quadrotors, but we are still light enough such that we can have those good scaling qualities, and we can scale, build the small robots in a swarm. So that's definitely something we are pushing on.
Okay, thank you.
Yep.
Yeah, may I ask one more question?
Of course.
Yeah, so it's inspired by the question from Hans. So I wonder, so talking about like a scale to a larger version, I wonder, so for the last actuator, you demonstrate the artificial muscle one. So you showed you combine like 4 units together to give the robot some additional ability to control a robust to avoid something like that, also to avoid collisions on that. So I wonder if have you ever think about add multiple artificial muscle together to build a kind of actuator arrays for like a different application? For example, what I'm thinking is like, for example, in the fish, a real fish, they have like a group of muscles dealing with different in different part of bodies. Can we use something like that to build a group of artificial muscle robot fish or something like that? Do you think it's a durable, or think it has a kind of function, a potential to do that, or you think it's impossible?
I personally, I definitely think it's possible, and I feel like in fact we are trying to build and especially a lot of my current colleagues collaborating on this project, they're definitely trying to take a scale from one soft actuator, simply making an array of them. And application, for example, is haptics. They put 10 in a clause and they try to do some sensing and actuation on human arms. So those are definitely very exciting directions. And I personally think now the reliability of a single actuator is quite good. It's definitely feasible to combine a lot of them to do interesting controls. And as you've said, maybe trying to have more complex mode for control. Although what I would say is, yes, making a lot of simple components to achieve a complex function is interesting, but there's also another thing that we can push is to learn about the nonlinear dynamics of those single actuators so that we can explore those nonlinear dynamics to have very complicated actuation mode. So I think we can push on both paths so that in one day, hopefully we can make some robot that consists, for example, of 60 actuators can do hopefully insect-like things or animal-like things that are very complicated. So yes, I think it would be a very interesting path to pursue.
I don't have any follow-up question.
Okay, yeah, Hans.
Yeah, just may I comment on this, because
yes, please.
Looking at insect control, it's mostly big power muscles and a number of very small control muscles that are changing the dynamic behavior of the system to change the mode shapes, basically, of the flying motion for control. So although that takes a lot of actuators, but it does take very small actuators. So have you done any work in that direction? I've been trying to, but I was wondering whether or not you have done anything like this.
So yeah, so I think we have noticed a little bit of that, and I think we have a lot of biologists trying to reach out to us for collaboration. So one thing, 2 years ago, we published a paper in Nature. We noticed that there is a nonlinear mode that can be triggered when the robot is sort of under large load. It will tend to buckle when it's trying to flap at a large load. And you can eliminate that mode by providing a constraint at certain direction. So if that's exactly, I think, what you have said, a very powerful muscle, but essentially a tiny little bit of force in one particular geometry direction can trigger a large behavioral change. So those, yes, I think so far we've been able to try to linearize those, trying to avoid those modes, but be able to use those modes will be super important in the future. Then the challenge would be, as you exactly pointed out, how to create an array of very tiny, not power dense or energy dense actuators just for triggering or switching between those modes. I would be honest saying that it's actually quite difficult for us to create very tiny actuators. Well, the difficulty we have right now is making the electrical connection sort of requires a fixed weight. So I can say each electrical connection for the soft actuator is about 0.01 gram, right? So if we make a 0.1 gram actuator, 20% of the weight is spent for building the electrical connections. So that really limits how small the actuator we can make. If eventually one day we solve that fabrication challenge, if we can make a lot of 1 milligram, 10 milligram actuators, I think that's when we are ready to say, now we have a lot of tiny small actuators. Now we can trigger those complex nonlinear modes in the actuator.
Yeah, I want to follow up on this. Actually, Chen asked the question, which is very similar to the question that I want to reserve for the last but since nobody's raised voice, I would just want to follow up. I know the time is ticking, and hence question. It's also looking at a fish body on a little bit larger scale, they have big muscles that can control the major mode of their angular motion, but they also have muscle that actually tuning the the fins, all the things. So on top of that, is to scale up from 1 to 20 to 60 and 100. So not only we need to control individually, make sure each individual quality is good, how to coordinating between each other is that you don't want each muscle working against each other. But you want to how they coordinating together, so in the way to induce a traveling wave. That's for me is right now it's quite difficult to think, and haven't seen much significant progress from my perspective. So I don't maybe I'm limited to my reading. What's your comment on that, Kevin?
Yeah, so again, I think you're pointing to a very exciting path for research. Being able to create a large number of soft actuators to collectively have some emergent behavior in those actuators are very interesting. I can give you one example, right? I think now there's already colleagues at Harvard trying to make an array of soft actuators and induce traveling waves in that array. And if you can induce a traveling wave, you can think about using it as valves, pumps, or sending signals, all of those things. I think those are, in my mind, sort of early prototype of thinking about how do you induce macroscopic complex motions using a large number of small individual actuators to achieve that. But yes, I definitely agree with you. If we have the capability in one day to build 10, 20, 30 actuators very efficiently and somehow understand their physics so that we have identify a couple of important modes that we can collectively control them, that would be very exciting. That's essentially how, in my understanding, how animals will work, right?
Yep.
Do you mind one quick question? Yeah.
Sure.
Yeah, very exciting talk. Actually, I can see a lot of common research interested from your talk. And also, actually, as mentioned in my previous email, actually, our group is working on the CFD part for the insect size flying.
Oh,
especially, you talk about you are looking for collaborations on the Dragonfly inspired flying robots, right? So actually, we have several papers about the flow simulation of the real Dragonfly, and definitely looking forward to collaborate with you. Just one quick question about the current design of the like a Dragonfly like robots. Right now, is a wing is kind of like a passive when you only controlling the leading edge of the wing, or you prescribe the kinematics of the entire wing.
Right, so it's similar to all the other robots that I presented today. So basically, all of them are sort of have one active degree of control, the other degrees of freedom is passive. Okay. So which means that, you know, the wing leading edge is exactly as what you mentioned, is actively controlled. The other dimension, the pitch rotation, is passively mediated by the compliant flexure. Right. That I think has been there for many years, and one of the reasons is limitation actuation. We really couldn't have a lot of actuator, a lot of small actuators in there, because that again cause a lot of connections. Therefore, lift to weight ratio of the robot will drop. So what we are interested in is, one, working around those limitations, but also thinking about passive fluid structure interaction. I think, in fact, this is motivated by reading a lot of the papers, in the sense that most insects, I think, mentioned that this degrees of freedom is passive. They only very occasionally use that control to do aggressive maneuvers. But when they're hovering or anything, this degrees of freedom is mostly passive to improve how efficient they are with flying.
Right, definitely. Yeah. Actually, in our group, we can do two kind of simulations. One is we just apply a torsional spring along the wing for multiple flappers, so that it can passively pitching depending on the prescribed leading edge motion. And also, we can also just prescribe an equation for the wing depending on the geometry, and then we just prescribe the wing motion and do the flow simulation. I mean, either way, we are capable to do the simulation. But one quick question is, for example, for the Dragonfly wing shape is very unique compared with other like a two-winged insects like a fruit fly or bumblebee. Actually, their wing aspect ratio is relatively longer. Yeah, and also, I mean, it definitely we can discuss it later. But depending on the wing structure, whether the flexibility right now is important to your robotic design, it is something important, because as the wing aspect ratio increase, there will be a strong tip vertex around the wing tip, which will reduce energy efficiency if the wing flexibility is not designed properly. Because for the real insect, like a dragonfly, when we shoot the high-speed video of the real dragonfly, we see their twisting motion along the wingspan actually can reduce tip vertex generation and increase their flying efficiency. But definitely we can discuss this question more in the future. But a very exciting work, and actually we are looking for some collaborators can do the robotics and design so that we can do the simulation. But thank you.
Sure. Again, all of those comments are really exciting. I want to mention, like, when I was undergrad at Cornell, I got into this field because my advisor, Professor Jane Wang at Cornell, works on dragonfly-like flight. So we know for a long time dragonfly have very complex aerodynamic properties, much more complex than what we are working on now, right? So we're really both looking for collaborations and waiting until we have some expertise, so we are confident enough to tackle those problems. So yes, yeah. I know there's many rich problems in this field, and I definitely look forward to talking with you more on those.
Very cool. Thank you.
Okay, cool. Thank you.
Okay, great. So I have to suspend the meeting because we already used too much time. So thank you, Kevin, for your great talk. Also have a lot of questions yet, but I will reserve those questions, send email to you.
Great. Thank you so much
yeah,
for having me. It's fun to share my work with all of you.
Yeah. Thank you everyone for attending today's seminar. This seminar is recorded, so if you want to look again, and you can find from our channel, from our website. So thank you again. Let's see you next week. Bye.
Okay. Thank you. Bye-bye.
Thank you, Kevin. Bye.
Bye-bye.
Thank you.